Hello, ERA users. Today I would like to discuss a number of the new features and capabilities of K&M's ERA software. In October 2016, K&M released ERA version 4, which features three major technical upgrades that users should be aware of. First and foremost, ERA now features a static and circulating temperature model. The temperature model can be used to predict downhole and flowline temperatures. The thermal engine also allows us to adjust fluid density and fluid rheology to downhole conditions. Drill string and casing metallurgical properties can also be corrected for thermal effects thanks to the thermal model. ERA also features a new hydraulic engine, which incorporates the Herschel-Bulkley, otherwise known as yield power law, fluid model. In order to compute downhole fluid behavior, ERA now includes characterization of the fluid composition, which is defined by the oil, water, and solid phases of our fluids. ERA now automatically calculates downhole fluid density based on temperature, pressure, and fluid composition. Downhole fluid rheology can also be automatically computed using one of our preloaded HPHT matrices or by entering custom HPHT test data. Lastly, ERA now couples hydraulic friction with our torque and drag computation. Users will notice an increase or decrease in drag depending on flow rate and/or trip speed due to hydraulic friction. Let's take a moment to briefly discuss what the new temperature model does. ERA's steady-state temperature model computes temperature inside the drill string and in the annulus for each operation in the well. The temperature engine takes into account the geometry of the wellbore, as well as the various materials we use in the well construction process, including casing, drill pipe, rock, fluids, and cement. The temperature in the well is computed based on the heat transfer to and from the formation, pipe, and annulus. Heat generated by the drill bit, torsional friction, and fluid friction are also taken into account. Calibrating the temperature model can be achieved by adjusting three different parameters. First off, the geothermal temperature needs to be defined. Since the geothermal temperature is usually our largest source of heat, it is the first place to focus when dialing in the model. The temperature profile can be defined as a simple straight line gradient or using one of ERA's more complex models that takes into account ocean temperature for offshore wells or permafrost for Arctic wells. Next, we must define the mud inlet temperature. Usually we define the mud inlet temperature as some function of the flowline temperature. ERA uses three different options for computing inlet temperature, which will be discussed later. Finally, we must define the heat transfer factor. This is a value that is used to take into account the unknowns related to fluid composition and annular flow behavior. This value can be determined empirically if flowline and downhole temperature data are available. In a few minutes, we're going to see where we manipulate these three parameters in ERA. Now let's take a closer look at the new hydraulics engine. ERA's new hydraulic engine features the Herschel-Bulkley frictional pressure loss model. This approach has proven to deliver reliable results across a wide range of flow geometries and fluid types. The new engine also features a more sophisticated algorithm that takes into account the impact that rotation has on annular friction pressure. The new model is based on extensive laboratory testing and field validation. The new model now accurately reflects the influences of annular velocity, rotational speed, pipe-to-hole ratio, and rheology. And finally, thanks to the circulating temperature engine, the new hydraulics model accounts for the influence that temperature and pressure has on fluid density and rheology. As an example of the new rotation algorithm in action, we have a case here where we tested the model's ability to predict the rotational influence on ECD in a very long horizontal well. K&M's old rotational algorithm treated rotation as an on-off switch, which is shown here in red. The new model, shown in blue, does a much better job of mimicking the actual behavior, which was recorded in green during a step rate test after reaching TD on this well. Now let's discuss downhole density changes. As most of you are aware, the density of the fluids that we use in well operations are sensitive to temperature and pressure. When we apply pressure to a fluid, its volume decreases and therefore the density increases. Conversely, when we heat a fluid, its volume increases and its density is reduced. It's important to take both of these phenomena into account when we calculate downhole pressure in our wells. These density changes are automatically computed in ERA using the characteristics that we have defined for the fluid and the downhole temperature and pressure that we've calculated. The starting point for all the computation is the density that we measure at surface under specific temperature and pressure conditions. That is to say that when we quote a fluid density in ERA, we must also specify what temperature that density was measured at. In the example to the right, we can see that an 80-20 oil-water ratio oil-based mud has a density of 10 pound per gallon at 70 degrees Fahrenheit, but that same fluid only weighs 9.6 pounds per gallon at 180 degrees atmospheric pressure. This is a key output in ERA and something to keep in the back of your mind whenever you're specifying fluid density. To illustrate what happens to fluid density under combined temperature and pressure, we have created a simulation in ERA. In this example, we have a 20,000 foot TVD vertical well where we're drilling a 12¼ inch hole with an 80-20 oil-water ratio oil-based mud that weighs 10 pounds per gallon at 75 degrees Fahrenheit and under atmospheric pressure conditions. In the first graph, we can see that the static bottom hole temperature is fairly hot at 375 degrees Fahrenheit. This would be considered fairly normal for such a deep TVD land well. The next graph represents the hydrostatic pressure in the well, taking into account the variable density of the mud in the hole. The graph on the right shows the surface mud density in green compared to the equivalent static density in pink. It is important to remember that the ESD does not show the local density of any particular layer of fluid, but rather the cumulative effect that temperature and pressure has on the entire mud column. As you can see at 20,000 foot TVD, the bottom of the hole feels like the mud only weighs 9.7 pounds per gallon. This is because thermal expansion is having more of an impact than compression due to pressure. Make a point to note that at the previous casing shoe, around 5,000 feet TVD, we have an ESD of approximately 9.9 pound per gallon. If I change the model and simulate circulation, we now see that the temperature profile in the well is much different than under static conditions. The dotted curve represents the annular temperature and the solid curve represents the temperature inside the drill pipe. We now see that the ESD curve takes on a very different shape. Due to a much hotter average temperature in the well, the bottom hole equivalent static density has decreased to 9.6 pounds per gallon. More importantly, shallow in the well, where we once had 9.9 pound per gallon ESD, we now only have a 9.5 pound per gallon equivalent mud weight. Surprising phenomenon such as this are important to model, and they will vary greatly depending on the geometry, the fluid type, and the temperature profiles in the well. Similar to the way density behaves, fluid rheology is also impacted by temperature and pressure. Increasing temperature tends to thin the fluid, and increasing pressure tends to thicken the fluid. These effects tend to be quite nonlinear. The overall impact of temperature and pressure is influenced by the type of base oil, the type of brine, and the type of additives that are used to build the mud. It must be noted that both oil-based mud and water-based mud rheology is impacted by temperature and pressure. ERA features a number of generic characterizations of fluid rheology at temperature and pressure. But for the most accurate results, it's best to perform HPHT rheometer testing on the specific fluids that you are using or planning to use. The HPHT rheology corrections are turned on by default in ERA, but can be turned off in the fluid dialog, which I'll show you in a moment. In the sub-up calculation screen, we now have a button called Fluid, which replaces a button we used to call Rheology. If I click on the Fluid button, a dialog pops up that allows me to define a great many properties pertaining to the fluid, including density, rheology, composition, and 3 different calibration parameters. We will discuss each of these features later on, but right now I just want to show you where you would turn off the pressure, temperature, rheology corrections if you wanted to do so. Simply click on the HPHT tab in the upper left-hand corner of the dialog. The HTHP tab reveals the test matrix that is used to characterize the fluid rheology under temperature and pressure. To turn off the temperature pressure effects, simply uncheck the Enable box. Doing so will result in the model assuming that the mud rheology downhole is identical to the surface rheology. You may have even noticed in the background how the ECD predictions change slightly when I disabled this feature. We will discuss the fluid dialog later on in this video in more detail. The last feature we need to discuss is hydraulic lift. ERA now couples hydraulic friction to its torque and drag computation. In general, circulation tends to reduce tension in the string due to the increased annular friction pressure pushing up on the string. This phenomenon explains why we tend to see different hook load readings when the pumps are on versus when the pumps are off, and why we tend to see that the hook load varies when we increase or decrease our running speed when tripping in or out of the well. For most operations, the hydraulic lift effect is fairly minor and there's not much consequence by ignoring it. However, for floated casing or tight clearance casing run operations, the lift force can be quite significant and it is important to take it into account. It's also important to note that when we back calculate friction factors from offset wells, our interpretation of the friction will generally be lower with the hydraulic lift effect taken into account. Therefore, it's important to make sure that all simulations are apples to apples, meaning that if we hindcasted a well to determine its friction factor and we had the hydraulic lift effect turned on, then we should also ensure that the hydraulic lift effect is enabled when we forecast future wells. Here we have an example of a very long floated 9 5/8 liner run that we're reaming into the hole. With the lift effect turned off, the hook load readings that we observe are dramatically lower than what we predict, by up to 40,000 pounds. Likewise, the torque that we observe is significantly higher than expected. When we enable the hydraulic lift effect, the predicted torque and drag now align much more closely with observed values. Had we not turned on the hydraulic lift effect, we would have dramatically underpredicted just how much push force would be required to ream this liner in the hole, and likewise how much torque would be required at surface to turn the string. In this example, we have a conventional casing run, meaning that the casing is full of mud and not floated like in the last example. With the lift effect turned off, the model does a good job of predicting the drag that we observe, and we back calculate an open hole friction factor of around 0.33 to 0.35. With the hydraulic lift feature turned on, the model still aligns well with observed values, but all the predicted drag curves have now moved to the left slightly, reflecting that the resistance that is generated by surge is reducing our hook load. The back calculated open hole friction factor has also reduced by 10 or 15%. What I'd like to do now is walk you through some of the ways that we manipulate the new temperature and hydraulics models within ERA4. One of the first primary inputs we can control is within the Earth Builder. If we click on the Earth Builder, you'll notice that there is a temperature tab, and the temperature tab brings up two different options that we have for manipulating the temperature model. The first and most important is defining our geothermal gradient. And in this example, I have an offshore well, so I've selected the offshore radio button. What the offshore geothermal temperature model allows me to do is define my average ambient temperature, the temperature at the bottom of the seabed, and the depth of the thermocline. The thermocline is defined as the depth at which below that point the temperature doesn't change. So the way I've defined this here is from 4,000 feet water depth to the mud line, the sea temperature would be a constant 40 degrees. Between the thermocline and surface, the temperature will gradually increase in a parabolic fashion. Below the mud line, I've assumed a linear gradient of 1.9 degrees Fahrenheit per 100 foot. Like all the other units in ERA, the temperature gradient and the temperature can be changed simply by clicking on the unit. Now for most of your wells and for land-based wells, just a simple gradient will be sufficient to define the temperature profile. And here we just enter in the average ambient temperature and the linear temperature gradient. In Arctic environments, we can use the permafrost option, which is somewhat similar to offshore in the sense that we define an average ambient temperature, which is usually fairly cold in Arctic environments, and the depth of the permafrost. And the depth of the permafrost, by definition, is where we reach 32 degrees Fahrenheit and we warm from that point deeper in the well. So from the base of the permafrost to whatever depth we're investigating, we'll have a linear gradient of 2.9 degrees per 100 foot, which is a fairly reasonable gradient for the North Slope of Alaska. The fourth option that we have for the geothermal gradient is what we call profile. And under profile, we can simply copy and paste a complex temperature gradient if we happen to have more detailed information about the subsurface temperature. The other set of inputs that we have to control is the way we define our mud inlet temperature. And the three options here are what we call heat retention, fixed, and inlet minus flow line. Now, heat retention is the most common, and by definition, what that means is the value that you enter here is the percentage of heat that is retained between the flow line and the inlet temperature. And heat is the difference between your ambient temperature and your flow line temperature. So if I had an ambient temperature of 70 degrees and a flow line temperature of 100 degrees, that would be 30 degrees of heat. And if I retain 75% of that 30 degrees, then I simply add that 75% retention to my ambient temperature, and that's how the model computes the inlet temperature. Now, alternatively, I can just define a fixed inlet temperature, which is not very commonly used, and it's really not technically very valid because the inlet temperature does vary and it tends to be a function of flow line temperature. So we try to dissuade people from using the fixed temperature option. The last option is just simply inlet minus flow line, and that defines a fixed offset between your inlet temperature and your flow line temperature. And that could either be warming or cooling depending on your well conditions. On a lot of deep water and subsea operations, the mud that is entering the inlet, it tends to be warmer than the flow line simply because the rig is warmer than the cold mud that is coming out of the riser. But for this particular operation, we're going to use the heat retention factor of 75%. By default, we use 90% heat retention, and most of the time, most wells that we've hindcasted, a very typical value is somewhere in the neighborhood of 85 to 90% heat retention. So that's a good starting point. Now that we've had a look at the Earth Builder, I'd like to show you where we can control some of the temperature simulations. If we just click on one of the sub-ops, let's say drilling the 9.5-inch hole in this example, I've arranged my plots here so that we can see a couple of the key features. And the first one of them is our temperature plot, and then of course pump pressure and ECD as well as ESD here in pink. And the reason why I've brought these up is I'd like to show you how we're able to manipulate the calculated temperature for different sensitivity analysis. Now on the temperature plot, if I double click, I'll be able to pull up the details, and you'll notice that I've got two different groupings or families of curves. One of the sets of curves is the downhole temperature, and the other is the flow line temperature. And in this case, our flow line is the cooler of the two, and our downhole temperature is the warmer of these two families of curves. And right now what we're looking at is sensitivity to friction factor, but I could also calculate the temperature sensitivity downhole on the right and at the flow line on the left by just adjusting our radio button. So sensitivity to RPM, sensitivity to flow rate, each has a different impact on the overall temperature profile in the well. Speaking of temperature profile, if I want to see what it looks like throughout the entire wellbore, I'd have to click on the snapshot plot. And within the snapshot plot, you can see dotted lines here represent the annular temperature, and the solid curves represent the temperature inside the drill pipe. And as I move the drill string up and down, you can see that the shape of that temperature profile changes depending on where the bit's located in the wellbore. So that temperature curve is not a constant thing. It changes depending on where we're at while we're drilling. You'll also notice at the bottom of the screen, we've got a couple options for temperature. For all drilling operations and for cementing operations, we default to calculating the circulating temperature profile. But for certain operations like tripping out or tripping in or running casing, what we may elect to do is use the static temperature model. And by clicking on that radio button, now all of my hydraulics and my metallurgical properties will be based on a static temperature profile, indicated here by this gold curve, rather than my circulating temperature profile. And for certain wells, that does make a significant difference. What I'd like to do now is discuss the new fluid dialog. And as I mentioned earlier, the previously named rheology dialog is now called fluid because it's more descriptive of what we're actually inputting in this box. So if I click on fluid, it'll bring up a great deal of information that we didn't previously have. And we'll just start at the top. I'll draw your attention to the fact that there's two tabs. There's a tab called fluid and a tab called HTHP. We'll look at the HTHP tab in a minute. At the very top of the dialog, we've got our library of different fluids, which defines the density, rheology, and then also what we're calling now composition. Composition is the makeup of the fluid. It is a particular base oil, it is a particular brine or water phase, and it is a particular solid. And if it happens to be an oil-based mud, we also have to define the oil ratio. So you'll notice here for my water-based mud entries, the oil ratio is 0. And if I scroll down, I've got some oil-based muds here. And by default, we assume that the oil-based muds have an oil-water ratio of 80. And that obviously can be adjusted down in the lower left-hand corner. So you could pick any of these fluids out of the library and then alter them to your choosing by adjusting the brine phase, the oil phase, and the solids phase, as well as my oil-water ratio. And I could essentially turn this oil-based mud into a water-based mud by just putting an oil ratio of 0. And I'm going to turn that to 80. With regard to each of these composition components, we've got a list of common types of base oils, common types of brines, and they will alter the density characteristics of the fluid under downhole conditions. In the middle of the screen, what we've got is our surface conditions, defining the density of the mud at a particular temperature and the rheology of the mud at a particular temperature. And at surface, by definition, we're saying that the pressure is atmospheric, so around 14.7 psi. Below the density input, you'll notice that we've got a chart of mud density versus temperature. Now, this particular mud was tested to be 11.2 pound per gallon density at 110 degrees Fahrenheit. And due to the composition of this fluid, if it were to cool down to, say, 40 degrees, at 40 degrees Fahrenheit, it would actually weigh closer to 11.5 pound per gallon. And likewise, if it was heated up to 200 degrees, it would weigh less than 10.9 pound per gallon. So it's very important when we're inputting fluid density that we're mindful of what temperature we mean when we say that this is an 11 pound or 11.2 pound mud. Just what exact temperature was that measured at? Likewise with your rheology, standard API test conditions for rheology are typically 120 degrees Fahrenheit, but if you are testing at a different temperature, you would need to alter this input box. We normally sample and test our mud using a fan 35 rheometer, and so the inputs here are our 600 through 3 RPM reading, and what the program does is a regression analysis on these 6 values, and it alters the Herschel-Bulkley parameters, our NK and tau Y values, which define this blue curve. So the blue curve is my calculated rheological behavior, and of course I've got my measured rheology in these little red dots representing my fan 35 surface conditions. If I've got good data points, then that blue curve will hit all the dots, and if my measurements were a bit erroneous, if I had a value here that just didn't make sense, then the shape of the curve would not really hit the values, and I'd know that there was something potentially wrong with my measurements. The other thing that we can do is define our fluid rheology just with the NK and tau Y. If you happen to know what those numbers are, you can input them directly, and then the 600 through 3 RPM reading will be calculated rather than taken as input. Down at the bottom, I've already mentioned the composition. And then the other input that we've got is calibration factor. We had talked about the heat transfer factor. This value is empirically determined if you have measured flow line and measured MWD information. Through trial and error, you adjust this parameter until your calculated downhole temperature and flow line temperature line up with what you observe. And the other calibration parameter we've got is the pipe rheology percent and annular rheology percent. Those numbers are used to adjust the surface conditions in order to get your pump pressure or your ECD to match measured values. Now, if we have a good HTHP matrix, in an ideal world, we won't have to adjust these parameters because we'll be taking into account the changes that happen to my surface mud under downhole conditions. But sometimes, either due to a fan rheometer that's out of calibration, or perhaps we don't have an HTHP matrix that's well defined, these numbers need to be adjusted in order to get your model to match what you actually observe. So if I was to input a value of 80, what that would mean is my fluid is 20% thinner inside the drill pipe than what I measure at surface, or what even the HTHP model predicts that it should be. Now, if I flip over to the HTHP tab, what this will bring up is my test matrix of the rheology of the fluid at different combinations of temperatures and pressures. And then we have a model that tries to fit a surface to these test conditions. And this cube on the left can be a bit difficult to navigate. What you need to do is right-click anywhere on the cube and hold down on that right-click, and then you can rotate the axis of this cube any direction that you want. If you need to zoom in, you can do that with your mouse scroll wheel, or zoom out. And what you're looking at here, if we just take a moment, one axis on the horizontal plane represents the temperature, the other axis represents the pressure. And our vertical or z-axis represents the fan rheology reading for different shear rates. And you notice that there's 6 curves. It might be difficult to see the 6th one because it's way down here at the bottom, but the gold represents my 600 RPM reading, then my 300, 200, 100, and down at the very bottom, maybe if I zoom in, we can see it, the 6 and the 3 RPM reading. And if the model does a good job of mimicking my test matrix, these surfaces will hit the points at all different combinations of temperatures and pressures. If for some reason my test matrix is full of invalid data, then I'll see that the surfaces don't match. On the right-hand side, what I've got is my operational conditions. So downhole, I've got a combination of pressure and temperature in the annulus, which is this dotted curve, and inside the drill pipe, which is the solid curve. Those downhole conditions compared to my test matrix hopefully are confined within the bounds of what I've tested. And each of these purple dots represents different values from within my matrix up here. If I was to be operating outside the matrix, then that would create an error flag, or an alert. I shouldn't say error, but an alert that it's possible that the model is going to be projecting erroneous rheological information, because we don't have any data to confine what the model comes up with. If we were operating at, let's say, 350 degrees Fahrenheit and 20,000 psi way out here to the right, then we wouldn't have much confidence that the model was accurately predicting the rheology. So what you would try to do is go and test your fluid at those conditions to confine the behavior to your operating envelope. If I was to click over here on the left-hand side over on my wellbore schematic and I move the bit up or down, what you'll notice is those teal curves change, because wherever the bit happens to be located, that is a different temperature and pressure combination in the well. And likewise, if I was to grab my depth reference line, this horizontal red line, when I move it around, you'll notice that the red dot on my surface here moves around, as it does on my matrix. As I move this dot around, it will alter its position slightly. It's not changing as much on the matrix as it is here on this operational envelope. So that's a useful thing if we're trying to interrogate what the fluid is doing at a particular point when the string is at a particular depth. And if I toggle between pipe and annulus, it will change the position of that depth reference line. I want to see what it's doing in the annulus versus what it's doing inside the pipe. So lots going on in the fluid dialog. If you wanted to turn on or off the HTHP rheological feature, you can just do that by clicking enable or disable. And likewise, if you wanted to put in your own HTHP matrix because you went and had your mud company do some tests, you just uncheck this link to library and paste in your own values. Link to library basically says use K&M's stock matrix, which is assigned to each one of these fluids. As you click on different fluids, it has different matrices assigned to it. So hopefully that clears up the new fluid dialog. few of the outputs that are quite useful now, if we happen to have turned on and activated our HT/HP rheology values, is a flow regime plot and a rheology plot. And what you'll notice in your snapshot plots now, along with temperature, you can investigate what the flow regime is inside the drill pipe, which is our solid curves, or in the annulus, which is the dotted curves, as well as each of our 6 fan readings. So gold would be our 600, and over here to the left, our blue would be our 3 RPM reading. Dotted, again, is for in the annulus, and solid is for inside the drill pipe. And you'll notice that as you move the drill string up and down in the wellbore, the shape and characteristics of that profile changes, as does when you change your base parameters. If I was to circulate at only 400 GPM, that would change the temperature profile and would therefore change the rheological characteristics as well as my Reynolds number. So the dotted lines here on our flow regime represent the Reynolds number in the annulus, and then the solid curves are Reynolds number inside the drill pipe relative to our critical threshold values. When we're in the red zone, that means that we're in turbulent flow. So inside the drill pipe, we have turbulent flow. Inside the annulus, we have laminar flow. Even with very high flow rate, it becomes quite difficult to get the annulus into turbulent flow. You will notice, though, that the temperature increases as I increase flow rate, which is a little bit counterintuitive. A lot of people expect the temperature to decrease, but because a large portion of our overall temperature is coming from fluid friction, in this particular case, we get an increase in overall temperature both at the flow line and at the downhole tools when we increase flow rate. It's also useful to play around with things like RPM if you wanted to test the sensitivity to rotating the string at different speeds. We could see what kind of impact that has on temperature, flow regime, etc. So quite useful output. The last control feature I want to share with you is some options we have in the settings dialog. And if we click on our gear here in the lower left-hand corner, it'll pull up our settings dialog. And you'll notice that there's 2 new options, hydraulic lift and metallurgical temperature corrections. Both of those are checked on by default. If you were to turn hydraulic lift off, then we would decouple our hydraulic calculations from torque and drag. And likewise, if you were to uncheck metallurgical temperature corrections, then we would no longer adjust the strength of our drill pipe or strength of our casing or the Young's modulus of our drill pipe or casing for changes in downhole temperature. So both of those options we leave on by default, but if you want to see the impact of either one of those algorithms, you can turn them off and do a comparative analysis. Up until this point, we had been looking at some of the workflow and dialogues from within planning mode in ERA. But if you have a file that you've converted into execution mode, meaning you're entering in actual data in the field, the workflow and some of the dialogues are a little bit different. I just want to make you aware of some of those changes. Here I've got the same well that we had been looking at, and I have my 9.5-inch hole converted to execution mode. Those of you that don't know how to do that, you just right click on any particular op. If this was a planning file, when I right click on it, it will be executed when I click execute. And right now what we're going to look at is the drilling sub-op. So we could either trip in, trip out, or drill. Drill is the middle one. When I click on that, this is a case where I'm drilling the entire interval in one run. I could drill it in multiple runs. We'll have a separate video that talks about how you manipulate execution mode. But here we have a case where I've got actual data from the previous casing issue down to about 22,000 feet. The plot here is our calculated flow line temperature in blue, our calculated downhole, our MWD temperature in red, and you can see the measured values in the little circles, little crimson circles and dark blue navy circles line up well with the model, as does my predicted ECD versus actual ECD and my predicted ESD. The pink curve is always ESD, equivalent static density, compared to my measured equivalent static density. So the model's doing a good job of mimicking static and dynamic downhole conditions. And then, of course, I've got my calculated pump pressure and my measured pump pressure. The difference here, when I'm operating in execution mode versus planning mode, if I click on the fluid, you'll notice right away that the fluid dialog has this little chain or link associated with it. When I click on that, what the link is referring to is whether or not my look ahead or forecast parameters, and I guess I need to explain that a little bit more. I've got actual data from my previous casings you at about 10,000 feet down to 22,000 feet. Beyond 22,000 feet, I'm forecasting. So I'm predicting or projecting what the loads will be. And I'm using all of these input conditions, an ROP, a weight on bit, a bit torque, an RPM, a flow rate, but also the fluid characterization. And the fluid characterization obviously is going to have an impact on hydraulics. What I would like to do is use the most recent rheology and density that I've measured while I've been drilling this well. Close this for a minute. In the data page is where I store my actual mud test and my off-bottom and on-bottom data that I measure while I'm drilling. So each of these mud tests, I've got a defined density at a certain temperature, and then of course rheological characteristics at a certain temperature. When I'm forecasting ahead, and I click on my fluid dialog, more likely than not, I want to use the latest and greatest mud properties, and that's what this little link button does. If I uncheck the link button, then I can alter these values, make them anything I want them to be just to see what would happen. But more often than not, I want to use whatever the latest and greatest numbers are. When I get a new mud test in and I enter that into my data page, it will update these parameters accordingly. If it was a different temperature or if it was a different density, it will get reflected here in my forecast. The other thing that I want to point out is that if you had multiple bit or BHA runs in this section, all of your composition and calibration factors and your HTHP matrix are going to be connected within that one hole section. We're assuming that you're using the same fluid as you drill this interval. Now, obviously, the density and rheology can change from point to point, but the base oil, brine, in general, the oil-water ratio, and of course our calibration factors shouldn't really alter as we drill a hole section. They can alter from hole section to hole section. Say for example, I was drilling 12 1/4 hole. I'm probably going to have different calibration factors than I would have in my 8.5, or in this case, 9.5 inch hole. So that's the way things work in execution mode. Just something to be aware of. That sums up the key features and changes for ERA 4. We believe that we've got a much better capability now within the tool. Hydraulics has been greatly improved, giving us a lot more versatility to model a variety of different things. Please let us know what you think. If you have any questions, if you have any feedback, if there's things that you would like to see done differently, we're certainly open-minded and can incorporate a lot of those changes. But don't ever hesitate to drop us a note or give us a call. You can contact me at bfoster2@kmtechnology.com, and we look forward to hearing from you.